Mathematical induction. Now, we haven't had any formal proofs in this course. It's mathematical induction, in fact, is the only formal mathematical proof that we do in the pre-calculus course near the end of the course. So let's take a look at this way of proving statements. Mathematical induction is primarily a way to prove statements involving natural numbers. And we want to show that the statement, whatever the statement might be, is true for all natural numbers. Okay? Two conditions must be met when we do this. And P here references the statement, by the way, that we're going to make. P sub 1, that means the first condition is to show that the statement is true for the first few natural numbers. Now, some folks try it for the first number. Let's say if the statement requires the natural number to start with 4 for the statement to be true, then you try 4, 5, 6. Make sure things kind of get started and they go in the right direction. Usually we look at the statements for all natural numbers as starting at n equal 1. Once we have that, then from statement the P sub 1, we will generate what we call an induction hypothesis. And then from that, we go to condition 2. Condition 2 is that, I should say P sub k plus 1 here. We need to show that this statement is true for P sub k plus 1. In other words, the statement is going to work for a finite number k. If it's going to work for first k terms, let's say, then it's got to work for the next one and the next one and the next one after that. That's what the second condition requires. So let's see how this is going to work. We're using an example. I'm going to use several examples. These are going to be different types of examples to show you how versatile this technique is for proving statements. So something that we have seen in earlier section is that 1 plus 2 plus 3 plus dot 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 all the way to n. Remember, we wrote this in sigma notation. I believe it was in section 1 that we did it. To n can be written as n plus 1 over 2. Okay, we want to prove this using induction. So let's do the conditions that I cited earlier. So P1, that means when n is 1. Let's see if this works when n is 1. Well, when n is 1, the way it works on the left side with the series means you only have one term in the series, 1, right here. Okay, the right side, n is 1, so it's going to be 1 times 1 plus 1 divided by 2, and this is equal to 1 by 2 divided by 2, or 1. It checks. Let's try it for n2. For n2, you pick up 2 terms on the left side. That's 1 plus 2. The right side, is it equal to 2 times 2 plus 1 divided by 2? 3 equals 3. It checks. Let me do just one more to get you into thinking how this works for higher ends. N3 means you pick up 3 terms in the series on the left. The right side is now 3 times 3 plus 1 over 2, which is 3 by 4 halves. And that's 6. The left side, 6 equals 6. So it looks like it's working, doesn't it? And you don't have to pick 3 ends for this to do, but you can pick as many as you like. So this would be like P1, P2, P3 was what I've done. There you go. That's P2, and this was P3. P3 means the statement when n is 3. Now, from this, we're going to create or what we call induction hypothesis. Okay, so let me write that. The induction hypothesis. That means a statement that we assume to be true. The induction hypothesis goes like this. We're going to assume that P sub k is true. What do we mean by that? Well, P sub k means when n is k. That means 1 plus 2 plus 3 plus all the way up to k. And here, by the way, k is less than n. Okay, up to a k. is going to equal to k times k plus 1 divided by 2. And that's our induction hypothesis, which we assume to be true. Keep that in mind. We assume this to be true. We take it to be true. Now, the next condition is we need to show that p sub k plus 1 is also true. That means the statement is going to work up to k, and it's also going to work for the next one after that. Now this k is less than n. N could be a huge number. It could be in the trillions. And k could be in the thousands or millions, whatever. These are huge numbers that we're dealing with because we're looking at the set of natural numbers, which is an infinite set. So we need to show this part, and that's where the engine of this work is. The key step is right here, showing this is going to work for the next step. Because P1, P2, P3 are easy, you just plug them in. P sub k is when you replace n with k in your statement. P sub k plus 1. Let's see how that works. Now, what does P sub k plus 1, by the way, looks like? That's when you plug in k plus 1 instead of n in your statement. 1 plus 2 plus 3 plus 4 plus dot 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 plus k plus 1 is the next term. We want to show that this is true. I'm going to put equal sign because we haven't shown that. We're going to show that this is equal to, on the right side, which is n plus 1, we're going to replace it for n is now k plus 1, and the one after that is going to be k plus 2 divided by 2. You see that? This last term acts as an n right here. Okay, so that's what that is. Now we need to work on the left side here. According to our induction hypothesis, remember we can assume the first k terms add up to k plus 1 over 2. So I'm just going to replace everything up to k with k times k plus 1 divided by 2 and add it to k plus 1. And at k plus 1, I'm going to write it as k plus 1 over 1. Now the LCD, I need to get LCD. I'm going to multiply top bottom by 2 here of the second fraction. And now I can combine the two fractions with an LCD of 2. The numerator is going to be k plus 1 plus 2 times k plus 1. And in the numerator now I can see a common binomial factor of k plus 1. Let's factor those. So I'm going to get k plus 1. And what's left over is k plus 2 from the numerator divided by 2. And that equal to the right side, that being the right side. Therefore, the proof is complete. Okay, and that's what proof by induction is. Again, you show that the statement works for however many values of n. You generate an induction hypothesis as a result, and then show that the statement is also going to work for the next element in the series. Okay, so there you have it. That's an example of proof by inductions. Therefore, I can say that the statement is true for all natural numbers. Perfect. And there we have it. So our first example. Let's take a look at another example. The other example is another formula that we worked with: 1 cubed, 2 cubed, 3 cubed. Remember this one? Plus n cubed. We say that in summation formation, that's sigma k cubed as k goes from 1 to n. And the formula we had for this was n plus 1 divided by 2 quantity squared. Again, let me see if I can bring this back up. It's right here in front of me. This one that we did in the earlier section. So we want to show or prove that the formula is true using induction. And again, induction doesn't show you how we get n plus 1 over 2 squared. It's just a way to prove the statement is true. So let's do our work. P1 is when n is 1, all right? Let me write that, when n is 1. So this is going to be 1 cubed. Will that equal to, the right side is 1 plus 1 divided by 2 quantity squared. On the left, 1 cubed is 1. To the right, 1 plus 1, 2, and 2 cancel, so I get 1 squared 1, and that checks. Let's look at P2. P2 means when n is 2. So we pick up 2 terms on the left side. Will that equal to, this time n is 2, 2 times 2 plus 1 divided by 2 quantity squared. The right side is 9, the left side 1 plus 8, checks. See that? So you can try this for different values of n. You can go P1, P2, P3, P4, and so on. Once it works for a couple of first couple of numbers, then we generate our induction hypothesis, and this is it right here. Assume P sub k is true. What do we mean by that? That is P sub k. That means 1 cubed, 2 cubed, all the way up to change n to k unto k cubed is equal to k plus 1 divided by 2 quantity squared. All right, so this is the only thing we can assume is true. And here's the challenging part. Show P sub k plus 1 is also true. Show the statement works for the next term in the series. So what does P sub k plus 1, the next term, looks like? Well, the next term is when you replace n with k plus 1. So I'm going to go 1 cube, 2 cube. I'm going to go up to the kth term like we did up here. And then the next term is one more term, right? That's going to be k plus 1 cubed. That's the k plus first term. We want to show that this is true. So does that equal to the right side? Change on the right side, we're going to change n to k plus 1. Next to that, n plus 1 becomes k plus 2, because you add 1 to k plus 1, divided by 2 quantity squared, and there you go. Can we show this? Now, like the one we did earlier, everything up to k cubed we can assume true. That is our induction hypothesis. So that means the left side up to k cubed can be replaced by k plus 1 over 2 quantity squared. And then to that, I'm going to add k plus 1 cubed. I'm going to give it a denominator of 1, so I'm about to add 2 fractions. Notice, this is the right side. Leave alone. We're not doing anything to the right side because we want to show the left equals the right side. All right. And let's work on the left side. So what can I do on the left side? Well, on the left side, the LCD is 4, isn't it? Because when you square 2, you get 4. So this is 4. That means I'm going to multiply top bottom here by 4 of this fraction. The numerator of the blue fraction is going to be k squared, k plus 1 squared. The numerator of the second fraction is 4k plus 1 cubed. Okay, now I can factor k plus 1 squared from the numerator, couldn't we? Let's do that. So I'm going to go k plus 1 squared. When we factor it from here, what's left over is k squared. That's what remains. What remains from the second expression, because we're removing 2 factors of k plus 1, the binomial. So I'm going to have 4 times k plus 1. I still have 1 factor of k plus 1 remaining, divided by 4. Now within parentheses, let's see, let me just rewrite this one. And within parentheses right here, we're going to have k squared distribute the 4 plus 4k plus 4 divided by 4. And the trinomial, this trinomial can be written as, I'm going to remove the color here, k plus 1 squared. The binomial form of this expression is k plus 2 squared, right? And you can see it is factorable. If you want to factor it, you can also do it that way. Plus 4. Write it as k, here's k, plus 2, and there you go. That's what you get. So it is factorable. And what can I do next? Looking at the right side, right in here. Indeed, we have the right side. We can write this whole thing as k plus 1, k plus 2, divided by 2 quantity squared. I just rewrote this as one expression, one fraction to the second power. And look at the right side. The left side equals to the right side, so the proof is complete. Okay? And so we say that the statement is true for all natural numbers. I'm just going to say statement is true. That's by induction. See how that works? So it's pretty simple. At least for the ones that we have done, it's pretty simple. It can get a little tricky when we work with inequalities, but let me do a couple of more examples that are different than these statements. Okay, my next example. In this next example, I just want to show this. I want to prove that the product of n, remember, n is a natural number. n plus 1, n plus 2, this product is divisible by 6. Okay, now, first of all, to clarify divisibility here by 6. So, for example, we say that 42 is divisible by 6 because I can write it as 6 times 7. Okay, let me use a color here. 60 is divisible by 6 because I can write it as 6 times 10. So to be divisible by a number means you can write the statement, in this case that, as 6 times another natural number. Okay, so let me write down what this means. To prove this is to, we want to prove, in other words, n plus 1, n plus 2 is 6 times a number, I'm going to call it times c. How's that? C is a constant. That's what c is. Okay, a constant. If we can do that, then we have proved this. So let's begin with P1, first condition, P1. So that is when n is 1. So when n is 1, this is what the statement look like. N is 1, 1 plus 1, 1 plus 2. Well, the product is 1 by 2 by 3, which is 6. And that is clearly 6 times 1. It's divisible. 6 is divisible by itself. Let's see if it works for P2. When n is 2, this is 2 by 3 by 4. Right? 2 plus 1, 2 plus 2. It's going to be 2, 3, 4. What's that product? 6 times 4, 24, which is 6 times 4. You see that? So far it's working. Let me do one last one. That when n is 3 now is 3 times 4 times 5. That's 12 times 5, 60, and 60 clearly product of 6 by 10. So we were able to show that indeed every one of those is product of 6 and a constant. Now from this we generate our induction hypothesis. So here's our induction hypothesis. We're going to say that we are going to assume P sub k is true. That is k, product of k, k plus 1, k plus 2 is equal to 6 times a constant c. Okay, 6c. We can do that. And we want to show this time. Now we want to show, and here's the challenge, show p sub k plus 1 is also true. Okay. So what does p sub k plus 1 looks like? That's when you change your n to k plus 1. So that means k plus 1. See, I'm going all the way up here. K plus 1. K plus 1 plus 1 is k plus 2. K plus 1 plus 2 is k plus 3. We want to show that this can be written as 6 times c. Right? That's what we want to show. And the only thing that we can assume true is this one. Correct? So how are we going to do this? Now, to show this one, I'm going to write, let's see. Okay, I have k plus 1, k plus 2. Okay, let's do this. I'm going to keep those two factors, and let's distribute k and 3 to both of those binomials. So what am I going to get? It's going to be k times k plus 1 times k plus 2. That's this distribution to both factors, right? And then I'm going to multiply 3 times both of those, plus 3 times k plus 1, k plus 2. See that? So I just simply multiplied the binomial k plus 3 times those two factors. Now, if you look at this statement, isn't that p sub k? Look at it up here. That's our induction hypothesis, true? So I can write p sub k. So I know at that point that is 6 times c, isn't it? Because of induction hypothesis. So my task is to show that this is also 6 times its own c. Let's say that's c1, that's c2. Its own constant. So, and is it? Well, so here's how we can work this one now. Now, because k is a natural number, right? So we know that k plus 1 and k plus 2 are consecutive. Consecutive means back to back, right? Therefore, if they are natural numbers and consecutive, therefore 1 must be even, don't they? Think about any two numbers, 7, 8, they're consecutive, back to back. One of them is even. Another numbers, 11, 12. I cannot go 11, 13. They're not consecutive. So if they're consecutive, one of them has to be even, correct? And of course, the other one is odd. We know that. One is even. Now, it doesn't matter whether k plus 1 is even or k plus 2 is even. Agreed? Well, if one of them is even, must be even, which from this, we get the conclusion that k plus 1, therefore their product, if one of them is even, their product is going to be divisible by 2. True? So for example, 11, 12. One of them is even. The product, whatever that is going to be divisible by 2. Means divide by 2 gives you a natural number. Okay. And there you go. Like 7, 8. One of them is even. The product 56 is divisible by 2, right? 2 times 28. And that's what we're claiming here. The key is that the product is divisible by 2. Well, if it's divisible by 2, then I can write this 3 as, 3 times that as, the product k plus 1, k plus 2 is, I can write it as 2 times, let's say, d. 2 times d. That's what divisibility by 2 means. So in effect, again, I've replaced that product with 2d. And then it multiplies by 3. Now look at 3 times 2. Isn't that 6? 6 times d. And again here, the constants here, c1, c2, d, whatever. these are all natural numbers. So I have 6 times C1 plus 6D. And I can factor a 6 here, sorry. I can factor a 6. And I get what? C1 plus D, don't I? Plus D. And there you go. This is just a natural number, right? This is just a number. So this is equal to 6 times our usual C. And we just showed that P sub, so from this, P sub K plus 1 is also divisible by 6. Therefore, the statement is true. So that's how the ones involving divisibility look like. Isn't that cool? There you have it. Now, let's do last one of this one, and we'll be done with this section. So for this one, I'm actually going to do a couple of inequalities. Okay, so for this example, because inequalities are tricky because they involve inequality, so we can create magical steps that will serve our purpose. So here's an example. If x is greater than 1, this is the hypothesis of this problem. It means if this is true, so for example, therefore x must be 2, 3, 4, and so on. But if x is greater than 1, and of course x is a real number, by the way, it could be 1.7, blah, blah, blah. As long as it's a number bigger than 1, then x to the n, because n is a natural number here, then x to the n will be greater than 1 also. And I know it seems obvious, it's like, well, try it. Put 3 squared is greater than 1, 9 cubed. See, it works. But that's not a formal proof. It shows that it works, but that's not the proof. So let's try P1. See if it works for N1. X to the first power, which is x. That would be greater than 1 by the hypothesis. This is true. Because that's what the if statement told us. Let's look at P2. P2 means x squared. Well, x squared is product of x times x, right? And that's going to be greater than 1 since x is greater than 1. True? Since x is greater than 1. So we multiply left side by a number greater than 1, so square of it will be greater than 1 also. So it works for x squared. Now, induction hypothesis. We're gonna, let me put in my general format. We're gonna assume P sub k is, oops, sorry, there you go. P sub k is true. What do we mean by that? That means x to the k power is greater than 1 if x is greater than 1. This is the only thing we can assume to be true. It's called our induction hypothesis. Now we want to show that this also works for the next value after k. Show P sub k is also true. And what is P sub k plus 1 is also true. What is P sub k plus 1? That means I need to show that x to the k plus 1 is bigger than 1. This is what we need to show. Okay, well, let's begin with our induction hypothesis, because we were allowed to assume this is true. So I'm just going to start with that. And then I'm going to multiply by x. Okay, you're going to multiply by x. So on the left side, we're going to get x to the k times x. And this is going to be greater than 1 times x, right? Because I'm multiplying both sides by x. And x is positive here. We're told that. So I don't need to change the direction of inequality. Okay, now, if x is greater than 1, which we were told in the beginning, right? In here, if x is greater than 1, then we can write x to the k plus 1. That's when you multiply these two together. Therefore, that's going to be greater than x, because 1 by x is x, right? But then we were told x is bigger than 1, and this is greater than 1, according to our hypothesis of the original statement, right? That was a given. Putting these two together, we just showed that x to the k plus 1 is greater than 1. So x to the k plus 1 is bigger than 1. And there you go. Therefore, the statement is true. And of course, you can say it's true for all natural numbers, but that's what we wanted to show right in here. All right, again, the challenge here, folks, is to show p sub k plus 1 is also true. Prior to that, it's pretty trivial, simple to show or work. Now, let's finish this off with one that's slightly more challenging. How about this one? For this next one, we want to prove, there you go, in this next example, we want to prove that 1 plus a to the nth power is greater than or equal to 1 plus na, when a is positive. Okay, so let's begin our first statement. That's when n is 1. So when n is 1, I have 1 plus a to the first power, which is 1 plus a. Is that greater than or equal to 1 plus 1 times a? That's, I'm working the right side. 1 times a is a, 1 plus a, and that is true, right? It's not greater than what it's equal to, so I check that. Let's look at P2. What does P2 look like? That's when n is 2. 1 plus a squared, is it greater than or equal to 1 plus 2a? Well, if we expand the binomial on the left, we get 1 plus 2a plus a squared, right? Square of a binomial. And because a is positive, you square it as positive, so you're adding a positive number to 1 plus 2a. That will definitely be bigger than 1 plus 2a, correct? It's bigger than 1 plus 2a by a squared. And we just showed that it works. It worked for P2. Same way you can show it for P3. Okay. Therefore, here's our induction hypothesis, p sub k. Let me again put it in my general format. Assume p sub k is true. So what are we assuming? So p sub k, that is, we can assume only 1 plus a to the k is greater than or equal to 1 plus ka for positive a. That's the only thing we can assume is true. What do we want to show? We want to show that p sub k plus 1 is also true. And what does p sub k plus 1 look like for this example? That's when we change k to k plus 1. And that has to be greater than or equal to, change k to k plus 1. There you go. And again, all we're saying is that, well, it worked for up to k. Is it going to work for the next one after that? So this is what we want to show, right? Okay, and I'm going to start with my induction hypothesis then. I'm going to say that 1 plus a to k, they allow me to make this presumption. There you go. I can start with that. That's a given. Okay, now what am I going to do? Let's multiply both sides by 1 plus a. And the reason is because I want to create 1 plus a to the k plus 1 power. Okay, And we know that this is going to be greater than or equal to the right side also multiplied by the same thing. I'm multiplying both sides of inequality by the same binomial. What do I have on the left side? On the left side, I have 1 plus a 2k plus 1. That's going to be greater than or equal to. On the right side, let's FOIL it. Let's FOIL. When we FOIL, we're going to get 1 plus a, right, plus ka plus ka squared. That's what we're going to get when we distribute, multiply two binomials. Now, I'm going to work this a little bit. I'm going to factor the a from that middle term. Okay. I'm going to get a times k plus 1 plus ka squared. Correct? Now, would you agree that this whole expression on the right side is going to be greater than or equal? Don't worry about that part. The fact that it's greater than, it will be greater than 1 plus k plus 1 times a. Agree? And the reason is because it has an extra term. So all of this is going to be bigger than just that, right? Think about the three terms. These three terms will be bigger than, their sum will be bigger than the sum of these two terms, right? Okay, and because ka squared is positive. Because k is natural, a squared is positive, so you're adding a positive number. And let's see what we have at this point. So at this point, the left is 1 plus a to k plus 1 is greater or equal to, let's see here. So I have, let me go back up here. I dropped something. Sorry, I dropped a 1. See right here? I'm sure all of you caught that one because I only changed k to k plus 1 times a. I entirely forgot about 1, and there it is. Okay, now it looks good. And the right side is indeed what this is. Look at that and look at that one. They're exactly the same. It's going to be greater than k plus 1, a plus 1. And so the proof is complete and this statement is true. This statement is true for all natural numbers. And there you have it. Proof by induction. And there, with that, we are done with this section. We only got one more section, one last lecture left for this course. And that's the next lecture will be on the binomial theorem. All right. Thank you for watching, everyone, and hope to have you again in another video of mine. Take care. Goodbye.